As Wahid mentioned, I'll take over at this point and talk a little bit about practical aspects and some applications. Um, Let me start really by just continuing right where Wahid and Usman left off and say some of the papers in the issue focused on the batch machine learning setting, as has already been mentioned. So, you can think of it trying to train some sort of predictor, whether it's a classifier or a regression model. And as Usman and Wahid both mentioned, that corresponds to solving this minimization problem shown on the right here, where essentially the problem is fixed during the entire time that we're trying to solve that problem. So in this case, n might be the number of data samples that we're trying to fit the model on. And so that's not changing while we are solving the problem. We have some fixed total batch of data set that we are fitting the model to. And as Wahid mentioned, there were papers in the issue that cover this sort of a setting where it's a fixed mini batch or a fixed batch of data, both in the centralized and decentralized cases. And I've listed some of those papers here. So on the paper by Gower et al., by Lee et al., Mokhtari and Ribeiro. So I guess Gower et al. Looks at variance reduced methods, as has already been mentioned. Lee looks at accelerated first order optimization algorithms. So that would be things like how do we incorporate momentum, as it's commonly called. It could be Polyak / heavy ball momentum or Nesterov momentum. Both of these first two papers would talk about just using gradients or stochastic gradients of the objective. The paper by Mokhtari and Ribeiro looks at using second order information. So things like the Hessian or approximating the curvature of the loss functions that we're trying to minimize. And then this fourth paper by Sahu and Carr actually talks about zeroth order optimization in the stochastic setting. And that's zeroth order means you don't even get a gradient. You only get to pick a point X, a set of model parameters, and look at what is the loss function at that point. And so often these methods end up trying to leverage some of the techniques maybe from the first order methods, essentially by using evaluations of the function at nearby points to estimate a gradient. That's one possibility. So this is so this is the batch setting, and this is all definitely relevant in practice. There's a lot of examples where we might gather a large data set and try to fit a model to that offline just in the batch setting. But there's also examples where we might, well, so before before going in that direction, let me actually mention one practical aspect that comes up in what Wahid was talking about for distributed optimization. He hinted at it, is that there's delays and potentially asynchrony. And so let me just explain that a little bit more. So I borrowed Wahid's figure up here. This is the master worker setup, but we could also talk about just a decentralized setup where we have multiple servers. In any case, when we're using multiple servers to solve a large scale optimization problem, then nodes are going to have to communicate. They're going to have to do some coordination, as Wahid mentioned, in order to solve that. They can't solve the problem in isolation because they don't have access to all of the data. Or in any case, even if each of them does have access to all the data, our hope is that by leveraging this parallel computing resources, we'll be able to solve the problem faster. Of course, whenever servers are going to be communicating, there's some delay in how long it takes to send one message from one server to another. There's also a delay involved in computing things like a gradient, and those delays might be different at different nodes. And they might be different at different nodes because it might be that the size of the data set being used to evaluate the gradient at different nodes is different, or the hardware might be heterogeneous. You might have some processors that are faster than others. For whatever reason, there might be heterogeneity in the system. And that leads to problems called stragglers, right, where you have one node that is slower than the others, whether it's because of computational reasons or communication reasons. And dealing with these delays and stragglers, if your method is synchronous, if we have to wait for all nodes to finish their gradient computations before we can collectively perform an update, that's going to potentially slow things down significantly. Essentially, we move at the pace of the slowest node. And so one natural way to overcome this kind of an approach is that we might allow for some asynchronicity or asynchronous updates in the way that we perform the optimization method. So we might not wait for all nodes to finish their computation. We might even just wait as soon as one node finishes its gradient update, it sends it back to the server, and the server will perform an update right away. But that leads to notions of delay, which need to be accounted for in the analysis. But on the practical side, this can actually speed things up considerably. And so the paper by Asran et al. Focuses on asynchronous parallel and distributed optimization. And I just grabbed this figure from that paper. It's illustrating an example of training a deep neural network on a system, I believe, with 256 GPUs. It's an image classification model being trained on the ImageNet dataset. And so this is a data set that has about 1.2 million training images, each of which has been labeled as coming from one of 1,000 different classes. And the model that's being trained has on the order of about 25 million parameters. So you can imagine 25 scalars, 25 real value, well, float 32 values that need to be communicated every time we have a gradient. So that's a pretty significant communication overhead. And so without going into the details, let me say that the red curve corresponds to a fully synchronous scheme where all nodes have to wait for everyone else to be ready before they perform an update. So you can see it gets to a good accuracy, but on the x-axis here, I've plotted essentially the loss that we're trying to minimize as a function of time, wall clock time. And so it takes a while to get there. The green curve corresponds to a method where it's decentralized and where each node only has to wait for a few of its neighbors to finish their computation before we proceed. And so we're no longer waiting for all of the nodes in the network to finish, just a subset, and that does lead to some speed up. But the blue curve corresponds to the asynchronous case where now each node is going to perform its update, it's going to communicate that, and then it's going to continue on without waiting for other nodes in the network. And clearly that one converges quite a bit faster than the others, finishing or achieving a similar accuracy in about, a reduction of about 1/3 of the time. And this can make a big difference in practice. Okay, so asynchrony is one issue. I had started to hint at before that another issue that might come up in practice is that we might not want to just gather a data set and train that offline, but we might want to do online machine learning, essentially dealing with streams of data. And this might be for a variety of reasons. It might be that we don't want to store all of the data, so we need to process it as it's arriving. Could be that we also expect the distribution of the data to change over time. And essentially, we want to track and make predictions based on kind of what's the latest distribution of the data. And so that leads to the streaming or time varying optimization type of a setting. There are two papers in the special issue that focus on this. One is one which Wahid mentioned, which is by Nokolby et al. And the other one is by Simonetto et al., which looks at time varying convex optimization. And I just wanted to mention, you might be thinking kind of streaming optimization or estimation. There are very strong kind of natural connections to some online estimation problems you might be familiar with, things like the Kalman filter. And often these time varying convex optimization problems or methods will have a similar flavor in the sense that they'll try to make a prediction based on how they think the distribution of data might be changing over time if we believe that it's not changing too rapidly over time. And so we'll make a prediction and then do some sort of correction. But this is a bit more general than the typical Kalman filtering setup. So let me continue on now. There are a few papers in the special issue which deal with applications to robot networks and energy systems. And it might seem strange to group these two together, but in fact, these couple of papers do touch on both. One is because both of these types of applications, one thing they might have in common is that when you're operating a robot network or an energy system, you often will need to make decisions in a real-time manner. And so this places some additional interesting constraints on the types of methods that can be used and yeah, on the performance of the systems as well. So one example that's shown here in the figures comes from the paper, I believe this is the paper of Simonetto et al., if I remember correctly. And so the problem is you have a robot at this position. You would like it to roughly follow this red trajectory to get to some destination, but each of these black circles corresponds to an obstacle that needs to be avoided. And so as the robot is moving through the network, it senses these obstacles and needs to adapt its trajectory accordingly. And that can be posed as an optimization problem. And what the figure on the right is showing is the error, the tracking error over time in two scenarios. One is the blue scenario is what they call unstructured, which is if you ignore the temporal structure, ignore that you just solved a similar problem, but that things change slightly because you learned about some new constraints as you're moving through this field. And the orange corresponds to the case where you're actually accounting for how, the optimization problem is varying smoothly over time. So it is changing, but it is structured in the sense that it's smooth over time, and you can exploit that to come up with a solution that has lower error and corresponds to a smoother trajectory through this space. Okay, and so if you're interested in more about robot networks, energy systems, or kind of in general optimization problems subject to real-time constraints, I'd refer you to these three papers in the special issue by Simonetto et al., Jalil and Shama, and Jakovetic et al. Last, let me mention that there are some papers in the special issue that look at optimization and learning problems in the context of inference in network systems. So one example shown in the figure here and taken from the paper by Mata et al. Is about graph learning under partial observability. So there may be a network system of interest, and there's some idea that you can observe a process evolving at each node in that network, right? But we don't know the connectivity among these particular nodes. So the gray region here shows that these are nodes where we don't know their connectivity. We just get to observe some signal of what's happening at those nodes. And then the problem is a sort of an inverse problem in that case. We would like to take this stream of data coming from each of these nodes and reconstruct how they're connected or how they depend on each other in some sense. And so this type of a problem is discussed in the paper, as I mentioned, by Mata et al., and also in the paper by Franca and Bento, a different sort of application. Okay, and so to conclude this part of the webinar, let me summarize a little bit and talk about some future directions and also some things that we didn't talk about today and that aren't necessarily covered in the issue. As Wahid mentioned, or sorry, as Uzman mentioned at the beginning, we did our best to come up with a broad variety of articles and also to have diversity in terms of regions where authors are coming from. Of course, there were space limitations and other constraints, which made it such that we couldn't cover all of the topics that we might have liked to. And I think there's some interesting topics and open directions worth pointing out if you're interested in this area. So one of those is scaling stochastic second order optimization methods. So we mentioned that there's a paper by Mactario and Ribeiro that talks about stochastic quasi-Newton methods. And it's a very promising research direction. But many of the methods, because they're second order, they rely on curvature information, still have some limitations in terms of the size of the problem that they can be applied to. And so, for example, in some deep learning problems where we might have tens of millions or billions of parameters, that starts to be an issue in terms of the scale. And so I think pursuing more in that direction is definitely one interesting direction. Theory and optimization for deep learning is definitely another interesting direction. And in particular, as Uzman mentioned at the beginning, often optimization methods try to exploit the structure in a problem. And deep learning is clearly an area that has had a lot of impact. And I think we're still very early in our understanding of what is the structure in those types of problems that can be exploited in order to do better optimization. And so that's an interesting direction to pursue as well. Another very relevant and timely one is in the field of privacy preserving machine learning. So Wahid had mentioned federated learning as one example. And so this is for sure something that's important and interesting, and it's a very active research area and lots of interesting directions to pursue there. Another topic which didn't get covered in the issue, but which is also super relevant, ties in somewhat to the time varying optimization, but not exactly, is optimization and reinforcement learning. In particular, reinforcement learning being where we're trying to learn a policy to make a sequence of decisions over time. There's very strong connections to optimization there. There's also been a lot of interesting work in the past couple of years and still a lot of interesting work to be done there. Active learning is another. So active learning being the field where, so in the examples that Uzman gave at the beginning and that we were talking about, and most of the papers in the special issue deal with, the assumption often is that you have a data set and that data has been labeled. So I mentioned the ImageNet data set as one example, a million images, and each of them has been labeled as coming from one of 1,000 different classes. But obtaining those labels is extremely expensive. And so the problem of active learning considers a formulation where you have unlabeled data and the algorithm itself can try to choose which samples are interesting to be labeled, to obtain labels, to get more information. And so that's another exciting and important area. The last one I mentioned ties into the last application that I talked about of inference in network systems. So graph signal processing has clearly been an area of interest in the signal processing community, as have graph convolutional neural networks for processing signals and data over graphs. And there's a lot of interesting optimization related questions that come into play for those types of directions as well. So with that, let me wrap up and say now I think we're at the point where we can move to the Q&A. And yeah, thank you for your attention so far, and we're happy to take your questions.